ring substitution reaction. These are mainly possible in the aromatic amines. Or here we can see the electrophilic substitution reaction. We know in anyway the maximum electron density is found at the ortho and para positions. Therefore, the substitution also takes place at ortho para positions. First one is the bromination. By using bromine and water at room temperature, the product will be a 2,4,6 tribromoaniline. Both ortho positions and para position will be substituted by bromine. The reaction can be controlled and we can prepare a monosubstituted product, such as when aniline is treated with an anhydride in presence of pyridine, NH2 will be converted into NHCOCH3. It is acylated, and that is the N-phenylene ethanamide, which on bromination in presence of acetic acid. Here para product will be the major product, and further on hydrolysis it can be converted into 4-bromoaniline. That is, monosubstituted product can be obtained by protecting the NH2 group. Next one is the nitration. Here nitrating mixture or HNO3 and H2SO4 is used as the nitrating mixture for nitrating the aniline. In strongly acidic medium, aniline will be converted into anilinium ion, which is a meta-directing group. So, in addition to the ortho and para products, here meta product is also obtained. It is a major product obtained here. 47% of the product will be meta product. So, here aniline when heated with nitrating mixture at 288 Kelvin, 51% of para product, 47% of meta product, and 2% of ortho product will be obtained. Here also monosubstituted product can be obtained, or para product alone can be obtained by protecting NH2 group by anhydride in presence of pyridine. Acetaldehyde will be produced, which on treating with nitrating mixture, para substituted product will be obtained, which on further hydrolysis can be converted into para-nitroaniline. So here NH2, this will be hydrolyzed. Next one is the sulfonation. Here the reaction with concentrated sulfuric acid forms anilinium hydrogen sulfate, which is heating with again sulfuric acid at 453 to 473 Kelvin produces para-aminobenzene sulfonic acid, commonly known as the sulfonilic acid. Amine, when treated with sulfuric acid, NH2 HSO4 will be produced, which when treating at 453 to 473 Kelvin converted into sulfonilic acid, or it will be converted into an ion known as the Zwitter ion. Here SO3H hydrogen will be shifted to nitrogen atom. Next one is the separation of mixture of aniline. There are mainly two methods for the separation of mixture of aniline. First one is the Hinsberg method. Here the mixture of aniline is treated with Hinsberg reagent known as benzene sulfonyl chloride and treating the product with the potassium hydroxide. So primary amine, when treated with benzene sulfonyl chloride, removal of HCl takes place and N-alkyl benzene sulfonamide will be formed, which on treating with KOH converted into a salt. Secondary amine, same reaction with benzene sulfonyl chloride, removal of HCl takes place and dialkyl benzene sulfonamide will be formed, which is a solid and which further will not react with the KOH, while tertiary amine will not react with the benzene sulfonyl chloride. Thus, we are getting a mixture of salt, a solid and tertiary amine as such. Now, the entire product will be extracted with the ether. So tertiary amine and the product of secondary amine, that is a solid, will be passed over to the ether layer since they are organic compounds, while the primary amine, which is salt, remains in the aqueous layer. Then aqueous layer and ether layer are be separated, and further aqueous layer will be treated with dilute HCl. So the salt, when treated with HCl, will be converted into C6H5SO2NHR, which on hydrolysis in presence of concentrated HCl will be converted into RNH2HCl and C6H5SO2OH, benzene sulfonic acid. This one again treating with sodium hydroxide gives the primary amine. Then for the recovery of secondary and tertiary amines, ether layer is fractionally distilled. Ether layer contains both tertiary amine and the product of secondary amine, which can be fractionally distilled, and tertiary amine passes over, leaving behind the solid dialkyl benzene sulfonamide. This can be separated by filtration also, since the dialkyl benzene sulfonamide is a solid. And this one, dialkyl benzene sulfonamide, when hydrolysis in presence of concentrated HCl gives R2NHCl, and which on treatment with NaOH gives secondary amine. Thus, the mixture of primary, secondary and tertiary amines can be separated by using Hinsberg reagent or benzene sulfonate chloride. Next method is the Hofmann's method. Here, let us consider a mixture of amines, that is primary, secondary, tertiary and quaternary amine is present, which can be first distilled, and highly volatile quaternary amine will be, non-volatile quaternary amine salt will be leaving behind the non-volatile quaternary amine salt remaining will be present in the mixture, primary, secondary and tertiary amines, and which is treated with diethyl oxalate. So we get different products. For primary amine we will get oxamide, which is a solid. For secondary amine, oxamic ester, which is liquid, and tertiary amine will not react with the diethyl oxalate. So the reaction is as follows. When primary amine, 2 molecules of primary amine treated with diethyl oxalate, it will be converted into dialkyl oxamide, which is a solid, and secondary amine converted into diethyl oxamic ester, which is a liquid, and tertiary amine will not react. Now the mixture contains solid and a liquid, and also the tertiary amine, which can be distilled. The tertiary amine being more volatile, distilled out and collected first. Now the remaining mixture can be easily separated by distillation or filtration. Both are treated with alkali to degenerate the original amine. So this one, when treated with potassium hydroxide, potassium oxalate and primary amines, 2 molecules of primary amines will be produced. Similarly, the ester on treating with potassium hydroxide, secondary amine will be produced. Thus, mixture of amines can be separated by Hofmann's method, in which the reagent is diethyl oxalate.